Hello everyone, welcome back to VLSI Toolbox channel. Today I'll be showing you the backend design of differential amplifier using gpdk90nm technology. This is the second part of the video. I request all of you to watch the first part so to get a continuity with this demonstration. So without wasting time, let's move into the demo and see how it can be done. I've shown in my previous video. So this is it from demonstration purpose. All the analysis you can do using this setup, that is go to environment, run AB extracted using AB extracted mode, switch view list. So this will run the layout view and you can do all the analysis, other analysis, whatever I have told earlier. So hope you have got all this information, valuable information. So this is the schematic of differential amplifier and these are the aspect ratio of each transistor. So I have made some changes so to make this layout as symmetric or matching layout. So using some matching techniques called common centered matching techniques, I'll be showing in this demonstration. So I have changed this uh, W by L ratio with 3 micro by 1 micro with a 4 multiplier. So to keep the overall uh, required effective W 12 micro by 1 micro. Similarly, I have used 5.85 micro each with a 4 multiplier to make 23.41 micro effectively. Similarly, 2.55 micro each for a W34 and using 2 multiplier I have realized this. So in this way I have changed this parameter by and introduced multipliers as a parameter. Using these type of things we can do matching layout. So without wasting time, go to the layout. So go to launch, layout Excel, create new, press OK. So layout editor is now booked. You can check the grid size first. So it is not set. So grid size of this PDK is 0.05, 0.05, 0.005 and 0.05 Y snap. X snap and Y snap is same as minimum minor spacing. So you have to set the grid first. Press OK. Now invoke the instances. Go to connectivity and write all from source. No need of PR boundary IO pins. Press OK. So it will come like this. So Shift F. You can see here all these devices has been generated with 4 multiplier. This is also 4 multiplier, 4 each, and these are 2 multiplier each. So suppose this is A device and this is your B device. So we will be using a pattern called ABBA. You can change the direction of the arrow. A B B to B device. Then again A, one A device. Next B to A device and B. So likewise you can check the alignment or arrange the pins accordingly. This is, you can see here, net 2. This is net 2. So you can flip this transistor horizontally and connect to net 2. It will align automatically. Next it is net 2 V out. V out is here. You rotate the V out. Now again here see net 2 is common. So in this way we can mark this is V out, this is net 2, this is net 2. So rotate net 2, this is net 2, this is net 1, and this is net 1. So you can rotate this. Now net 2, this is again net 2 common. Just shift it. So in this way you can make the alignment. By pressing A you can check the alignment. In layout, alignment is very much important. Similarly we will do, this is suppose B device and this is A device. So A to B device, then A, again B to A device, then B. Now check the nets. I base, ground, ground. So you rotate this. Okay. Next this is ground. This is net 2. So rotate this. This is ground, ground common. This is ground. So I flip this. I base, this is I base, this is I base. So I rotate this or flip this. This is ground common. So in this way we can arrange this. Check the alignment. As you can see, this is IVAS, this is also IVAS, gate are short. You can do it as like this also. This is net 2. This is net 2. Or you can place it like this also, no issue. So press A to check the alignment. Press A. Okay. Okay. Now do the upper load transistor. So there is two multiplier. You can use interdigitization method also. So or command centered method, whatever you want. So first A device, this is B device. So first B A. A. So rotate this, flip. Similarly, B out is there. Rotate this. This is VDD. This is also VDD. Okay. Try to make it symmetric. Now let's start with the input pair first. So, metal 3, Control Shift W, metal 4 or metal 2. Okay. Now check the gates. Press O for via. I need stack via. Poly to metal 3. Not use single contact via. Minimum 2 contact should be used. Now connect. This is being minus. Again, try to keep it symmetric. Next, B in plus. With metal 3. So in this way inputs are connected. You can reduce this by pressing stress symbol, that is S. Now complete the remaining connections. Before that, let us make this ring for uh, body biasing. Okay, let me do this also. Since all gates are shorted, we will do with single via. Okay, this will be fine. Check alignment. Whenever you move any instance, please check alignment. Okay, next press O and place a via here. I think this is the IVS. Yes, IVS. I need to short this. I think this is IVS. Yes. Next with the metal 3 also you can do. Similarly, is shorted now. Now with metal 1, just connect this because this is IVS need to be shorted. Again, you have to short this one. So this is IVS. Connection is complete now. Similarly, these are all net 1. So gate are shorted. You can connect with a single via. Only V out from this and net 1. Again, via. Try to avoid M1 because it has highest resistivity amongst all the metal. Use higher metals for longer tracks. M3. So it is now shorted. Now before going to design or do layout further, let us give the body bias ring. So everything is learned now. Now create MPP guard ring PTAP for NMOS. You can make the edges So in this way I have connected the body pin. Now I will connect the ground pin of NMOS. This is the ground pin. Ground pin. Now I will do all these remaining connections. Similarly for this also you can do guarding placement. This will be end tap, but in this case we cannot keep gap between the two. Well, we have to connect the wells. As you can see, this is a pink color. This pink color is the N well. So we have to keep the N well within the limitations. You have to do it very carefully. Now it's straight line. Now you just mark the okay. So this is a BT ring. You have to carefully see this ring in case of NMOS or PMOS. Okay. Now ring placement for body biasing is done for both the most types of MOSFET. Let's do the other connections, remaining connections. So this is net 1, this is net 2 and this is net 1. So place the via 1, so with MEM3 you can draw these middle lines. Next is net 2. This is net 2. take different metal or V out. Similarly, V out. Net 2 and net 1. Now net 1, now let's join. Let's change this to metal 2. Now let's connect. So in this way, I finished the input pair MOSFET connection. Next, let's do this. Have the VDD. Let's do V out. So V out is connected. Next, we will do net 1 connection. So this is net 1 connection. This whole block can be bring a little bit lower, closer to this ring also can be. So these two blocks are connected. Next, the remaining is this one. Net 2. net 2. So this is for net 2 connection, like middle 2. Let's stress this layer and align with this layer. So net 2 is connected now. Next remaining net what? JND is connected, IO is connected. I think all connections are done. All connections are done. Let's check the DRC ones. For that, go to Ashura, run DRC. gpdk90 has to be selected. Run it. So annual to annual spacing. Let's check it. This one. So for that, I will recommend annual layer padding. Press R. So there will be no spacing issue. Next, this one. So for that, poly to poly gate spacing is 0.012. Let's check it. So in this way, you cannot do the corrections. Let's remove this. Connect with metal one itself. Similarly, remove this. Connect this with metal one. Okay. Now this is also create problem. Now I am doing the connection using metal one. Press R. Metal 3. Now let's check the DRC again. One is remaining. Metal 3 to metal 3 spacing 0.02. Why is the problem? So metal 3 to metal 3 0.25. Error how much is going? Check save. Again run DRC. No DRC error found. So DRC is passed. Now before going further, let's check the net once if everything is connected or not. Net 1 is connected. I think so. I think it's connected. Now select the layer level. Metal 3 level. Press L. B in plus. I bias. Select the font. B in plus. I bias. Next. Metal 2. Metal 2 level. B in minus. And VDD ground and V out is remaining. So metal 4 level. VDD and ground. Metal 1 ground. Save. So I have given the leveling. Now let's check for LBS. If everything is fine, then we will clear the LBS. So LBS is cleared, no error. Now we will go for parasitic extraction. So for that, Cadence new tool for newer version, we will have to install Quantas. So for Quantas, go to run Asura Quantas. It will check the RCX. Go to extraction RC. Reference node has to be given GND. Filtering power net you have to give BDD and ground net GND. Rest things are kept as it is. Here extracted view and run the packs. So it is created now. So you will find one view created at the library that is called ab underscore extracted. Now with this view we will simulate our test bench to check the post layout output. So go to this TB and click the schematic. Now check if all everything is perfectly ready. Now go to launch, load session. If you have saved previous state, you can load that state. Then SA gain and DC analysis also there. So first of all, we'll check the environment. Here you can see this is spectra. So now it will simulate using the schematic. So keep on append, simulate. So either I think model file path is not properly given. Again run, and now it is running. Now go to results direct plot, gain and phase, V out by V in. So this is the output of tree layout. This is from schematic. Gain underscore schematic. So it's from schematic. Now without closing this window, go to setup, environment, type ab underscore extracted. Space, okay. Now run it. This period is not required. Go to result direct plot, gain in phase, P out by P in. So this phase is not required. This V out is also not required. So this is the gain from layout. So gain underscore layout. If you change this color and merge it, you will find less variations, almost zero variation. And if you open this, you will see layout view is opening. So this is the layout view. We have simulated using AB extracted view, that is coming from layout. You can see the parasitic generated. If you check manually, you will find some capacitance. Here you can see some resistance is generated previously from AB extracted view. Using this view we have simulated. We have included parasitic capacitance and resistance at our simulation or in our simulation. So this is it. You can see resistance here, capacitance here generated. So this is the demonstration of post layout simulation of gain. In this way, you can simulate any other parameters such as slew rate, PSRR, transient analysis, everything can be simulated using this, keeping this environment to AB extracted mode, which will take the layout parasitics into account and simulate the output. So this is it from the demonstration purpose. Hope you have find some valuable information from this video. Please share and subscribe my channel for more such videos.